recording. Okay, so I'll pick up from where I left off. So as I said, I have a background in economics and statistics. I really like the statistics part more of it. So in my master's, I went more into that, and I went more into actual development and writing a lot of R, which was sort of getting a lot of traction back then. And that's what brought me into the world of software development and eventually into Microsoft. And now it seems as if machine learning and R and big data is getting more and more popularity, also in the software development world. So I feel like that I can finally use what I actually spent 5 years studying for my actual work, which is nice. I have a Twitter account, and you can find me at my username SebastianBK. And I also have a blog, sebastianbranders.com, where I upload all kinds of stuff. And I think I'll upload this presentation if it's not going to be so bad that it's not worth watching afterwards. Okay, so let's have a look at what we're going to speak of today. We'll speak of big data from Microsoft's perspective, and I think it's relevant to actually understand how Microsoft sees big data and how, because it's obviously influenced the way that we've built our tools, and I think it's worthwhile understanding that when you actually work with them. We'll then have a small quiz, man versus machine, to lighten things up a little bit. I think they've been stressed enough already this afternoon, and I can see that that apparently this slide of my presentation was not updated. So this is supposed to be introduction to R. I don't know why this is messed up. I will speak a bit about the Hadoop ecosystem and then have an introduction to Microsoft Azure and one of our specific services running in Azure called HDInsight. We're not building a recommendation engine, but we're using R in the cloud. And then I'll give you an introduction to another service also running in Azure called Azure Machine Learning. And then in the end, we'll wrap everything up. Does it sound fine? Okay. I think given the very stressed afternoon, I might make a mistake here or there. So please just answer questions and correct me if things do not make sense. Okay. I think in order to make a really good presentation, we need to work with each other here. So first of all, introduction to big data. So from Microsoft's perspective, we see these 6 big trends that are sort of defining the space. We see this explosion in devices. We see this ubiquitous connection. Jesus Christ. We see this ubiquitous connection becoming more and more popular. And when I first stumbled upon this word, I was kind of confused by it, and I translated it to Danish using a dictionary. And I think the best translation of the word is really allestedsnærværende. So we've got this allestedsnærværende connection, which is driving up more and more traffic, and the web traffic we see in the world is a good example of that. We see this rise of social networks and sensor networks, and all 4 of these green trends are all factories of data. And on the other hand, we see the trend of cheaper storage and faster CPUs. So this increasing amount of data that we're seeing in the world is now becoming more accessible and easier and cheaper to process than it used to be. And I think that's why we really see this trend now and not 10 years ago. If you look up the definition in Wikipedia, big data is a collection of data sets so large and complex that it becomes awkward to work with them. And I think the keyword here is really awkward, because it's not, theoretically impossible to work with your data on your own PC or whatever tool you might have, but it might become awkward or very slow or not very feasible to do it in that way. So that's a difficulty that we try to solve with some tools, and one of those tools is HDInsight and Hadoop in the cloud. The solutions that we have to these difficulties deal with complexities such as volume. So we might have a good tool in our own PC that might have, a quad-core i7 processor and maybe 16 gigabytes of RAM, but if we have like a very large data set, it still might be unfeasible to run it on our own PC. We might have a very a wide variety in our data structure, and also we would want stuff to be fast, even though we've got a lot of data and a lot of variety. If we then can solve these solutions, then we'll be able to answer some deeper questions that we couldn't answer before, such as what's the social sentiment of my product? A question that we might be able to answer by putting together a lot of social data and analyze it in a cluster like Hadoop. Another question could be how to optimize my services based on patterns of weather and traffic and so on. Once again, we're dealing with large amounts of data that we need to process somewhere other than our local workstation. And also another question might be how do I better predict future outcomes? So these are the things that we as Microsoft see, and I think it'll make sense why we build our products and our services the way we've built them when you sort of like rethink or keep these things in mind. Like, this is what we see, and this is the reason why we've built our products that we have in our cloud. Good. Sort of sets the baseline. Hope everybody agrees with what I said so far. To lighten up a little bit and to get a good start to the presentation, I thought it would be fun to include a small quiz. So do you remember this show, Versus on DR? I don't think it was that popular, at least not compared to X Factor, but it was on Friday night or Saturday night, and this was the TV show host, and then during the 1 hour that it ran every Friday or Saturday night, the TV show host would present a bunch of different challenges, and then the audience had to guess which competitor in the challenge would win. So one challenge could be, we've got this pile of dirt over here, or this pile of sand, and we have 20 school kids and then one huge industrial machine. And then you would have to guess if it would be the 20 school kids or the huge industrial machine that could move the pile of sand the fastest from point A to point B, and then you would have to guess, basically. So I thought we would do a challenge like of a similar nature. It's not going to be 20 school kids against the machine. It's going to be the entire population of internet users against the machine. And so the challenge is, what's going to generate more data, or who's going to generate more data? You have any suggestions? It's going to be people or machines? Yeah, you think machine? Yeah. I think that might be a wise choice. Let's see. So if we actually do some calculations, if we take one person and we say that person's going to tweet and just constantly tweet for 100 years, he's going to write 140 characters per tweet. There's not going to be any metadata on the tweet, such as the date or the location. It's going to be encoded with UTF-8, so 1 character is equal to 2 bytes. He's going to write a tweet every 10 seconds, not stopping at all, like not going to the bathroom, not sleeping, not anything, just tweeting. He's going to tweet around the clock. He's going to use the maximum amount of characters available, so the 140 characters per tweet. And then we'll give him some cola just to keep going. So that's 280 bytes per tweet. If we multiply that by 3,600 seconds in an hour and then divide it by 10, because he's only writing a tweet every 10 seconds, we get a little over 100,000 bytes an hour. We then again multiply that by 24 for the 24 hours in a day, and then 365 for the days in a year. And we get that he generates 883 million bytes a year. We then multiply that by 100 years, and that gives us 82 gigabytes. So if one person dedicates his whole life, and even more, because who's going to live 100 years, not doing anything but tweeting throughout his entire life, he's just going to generate 82 gigabytes. If we then take that number and multiply it by the 3 billion internet users we have in the world, according to the latest numbers of March 2015, we're going to get that the entire population of internet users, almost half of the world, tweeting for 100 years, not doing anything but tweeting, well, that amount of people is just going to generate 230 exabyte. Okay? Now, that's the people. If we then take its competitor, the machine, do you know this guy? Yeah? What is it? Yeah, it's the Large Hadron Collider. And if you've not seen this picture before, you can see there's a small guy standing right here. So it sort of gives you an idea of how big this thing is. The Large Hadron Collider is the largest and most powerful particle collider and the single largest machine in the world, built by CERN. And this thing generates 300 gigabytes per what? Per second. This is insane, right? They actually can't handle all of that data. It's just too much. So they put in some hardware filters, because software filters, they're not fast enough to keep up. So they've built some hardware filters to only take out what they think is interesting, and that amounts to 300 megabytes a second, which is still a crazy amount of data. If you do the same calculation, you get that this single machine over 100 years will generate 881 exabytes of data. So if you compare the two numbers, it's just, staggering. We've got one machine which realistically could generate this amount of data over 100 years, and compare it to 3 billion Twitter users, which, well, these people wouldn't even be able to generate that much, because it's not really that realistic that anybody would tweet, 24 hours a day throughout 100 years. So the winner is, of course, these sensors and machines that we see around the world. And I think, having this in mind when you actually develop something or analyze data, I think it's quite relevant. Now, if we would want to feasibly work with data of this size, we need tools that can handle it. And a great tool that's getting a lot of traction right now is Hadoop. Has everybody heard of Hadoop here? Anybody not heard of it? Yeah, Simi. How many actually have, or how many has a Hadoop cluster available? One person. Yeah, so, yeah, two maybe. So that's the typical picture I see. Everybody's heard of it, but nobody really has access to it or has worked with it, because, like who's got 20 computers that they're not using for anything, and like who's got the time to install everything on top of it? Unless you've got a really good business case or work for a company where a business case might exist to actually set up a Hadoop cluster, it's very unlikely that you would have access to one. And that's the thing that we would like to change in Microsoft. So Hadoop really beats SQL Server or any other RDBMS when it comes to data and data processing of this nature. That's why I've got this elephant trying to beat SQL Server right there. Hadoop is actually the name of the original founder of Hadoop, or the original inventor of Hadoop. Is the name of his son's favorite toy, which was an elephant called Hadoop. So that's why it's got its name. Do you know, like everybody here knew what it was? So I would like to actually ask you, could you say some things about what you think it is? Yeah.
Algorithm.
Algorithm? Yeah, maybe. Yeah. Some of it is an algorithm. Yeah.
An optimized database.
Yeah, you could say an optimized database. It certainly serves data, right? Yeah.
Runs in parallel.
Parallel, yeah. So the algorithms that we have, MapReduce as an example, would run in parallel. Yeah.
Can handle unstructured data.
Yeah, very good for unstructured data, right? Yeah. Any others?
Isn't that like more ecosystem that combines a lot of stuff? So we cannot say like it's just a framework or like algorithms.
Yeah. So it's everything. Like it is all of those things plus more combined into this ecosystem. And that's actually why I took this slide with me, because when people mention Hadoop, they actually think of more things, just like you guys said here, right? I would say, or I would argue, that at its core, it's about having a distributed file system across a number of nodes or across a number of servers that you would set up in a cluster. And then on top of those nodes, you would be able to do some data processing, originally with something called MapReduce, right? So the idea is that you can take commodity hardware, very cheap hardware that you could buy on eBay or at some cheap hardware vendor, and then you would put all of that hardware together in a network, and you would then install Hadoop on top of each of these nodes. So you've got this cluster of both data storage and processing power. So those are the two core things. We've got distributed storage plus distributed processing. I think those two things together really defines Hadoop at its core. So the idea of distributed processing is great because it allows us to put an abstract layer between the actual physical disks that might exist on these computers that we've put together in the network, and then the interface that we're using for speaking or communicating with the storage layer. So as an example, let's say we've got 20 nodes in our cluster. Each node might have 4 or 5 disks, and then this data we want to put into the cluster. We don't really care about if it's on disk 3 on server 14. We don't care about that. We just want this simple interface of putting in data and also extracting data from the cluster, and then it's up to the cluster itself to define or to decide where we actually place this data. There's some great ideas built into that where we can, increase redundancy so that all pieces of data that we actually have in our system is replicated thrice. So we're sort of resilient to failure of disks, and that's one great part of it. It's actually a lot deeper than that, but I think on an abstract level, HDFS simply provides us with an abstract layer for that can work as a file system for us, even though it's actually much more complicated underneath. We've got this idea of distributed processing, mostly with MapReduce. Has everybody heard of MapReduce? Anybody not heard of it? Yeah. Could anybody say what it is?
Algorithm?
Yeah. That's what we got. Great answer. Yeah. 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 So it's, I think I like to think of it as a framework for algorithms in some way, or a way of, processing data in parallel. So it's this thing that's got a mapper function and a reducer function. And I actually have an example, the famous word count example that I'll go through. So if people have not heard of this or understand it in detail, we'll go through that so everybody's on the same page. So around those two core components of Hadoop, we've got a bunch of other stuff. We've got Hive, a very popular tool for querying or accessing data from the Hadoop cluster using a very familiar SQL-like language. We've got another thing called Pick Latin, which was developed by Hadoop, and it's sort of a way of scripting data against our database. We've got this NoSQL database that can live inside of Hadoop called HBase. And there's a ton of things in this ecosystem, and every day there's another project that relates to Hadoop in some way or the other that's popping up. Well, the things we'll be using for this example would be the two core components, HDFS and MapReduce. And then if you look to the very top, you see three green boxes, and the one in the middle, the one called stats processing with R Hadoop, is what we'll be using to execute R scripts in our Hadoop cluster. Okay, things okay so far? Not too confusing, not too complicated, too easy? For some people maybe, for some people not. So a traditional Hadoop cluster, should I go through this, or is everybody okay with this? Somebody would like to understand how it works underneath? Yeah, okay, so we'll take, I think I'll explain this from how it originally started out as working. So this is from a very version 1 kind of thinking. We are up to version 2.6 now in Hadoop, and things have changed a little bit between version 1 and version 2 and gotten a little more complicated, but for a good reason. But just to understand how it works at its core, I think we'll go through the very basic example of it. So to work with the Hadoop cluster, we've got a client, and the client is me and my PC, right? I want to do some sort of data analysis on top of some data that I might have in my system. And to do so, I would interact with a primary node or a secondary node if my primary node is down, and a job tracker. Traditionally, the job tracker was very much coupled with the MapReduce idea, the MapReduce system. And that's one of the things that have changed between version 1 and version 2. Those two things have been deep coupled. But for now, let's just assume or put an equal sign between the job tracker or the resource manager and MapReduce. So the job tracker would be responsible for the distributed data processing, and I've put MR in parentheses for MapReduce, whereas the name nodes would be responsible for the distributed data storage through HDFS. We've then got a bunch of data nodes in our cluster, and there can be almost infinitely many of these. We've got examples of enormous clusters in the world. I think Yahoo is up to, I think, more than 50,000 nodes in their Hadoop cluster, if not more, I can't remember. And the idea with each node is that they're connected, well, to the cluster. They've each got their own storage layer, so they've each got their own disks, but they've also got CPUs, obviously. So they can both offer storage and processing. And then our job tracker and our name nodes will be responsible for handling both the processing and the actual storage. In a HDInsight world, in the distribution that Microsoft has developed for Hadoop in Azure, we actually do not have individual disks or physical disks attached to physical data nodes in the cluster. Instead, we've got this common storage layer offered, or which is provided by Azure Storage or Azure Blob Storage specifically. And so if you've worked with Amazon, that layer is very similar to Amazon S3. So we've got this storage layer that's not dependent on the individual nodes or the individual hard disks of the nodes. I think I'll just skip the difference between the MapReduce architecture between version 1 and version 2, because it's not really that important for our discussion on R, which I'll get to in a little while. It's fun that you've all actually heard of Hadoop, but only that that only 2 of you have actually worked with it. But it's very much up in, it's very popular right now, and it's trending very much, and I'll show you some fun statistics of that. A quick look at the timeline. It came out, or the original idea for the HDFS, or the Hadoop Distributed File System, came out when Google published its Google File System paper back in 2003, so almost 12 years ago. The following year, they published their MapReduce paper, and then there was this guy, Doug Cutting, together with Mike Caffarella. They took a look at these 2 papers and thought, that's a great idea. Let's make our own implementation of that and call it Hadoop. So that's what they did 10 years ago. And then a lot of years passed by. It didn't really catch any traction until 2009, 10-ish. And Microsoft had taken a look at that as well. So we started working on a distribution for Azure, a cloud-oriented distribution named HDInsight. And it came out as a technical preview 2.5 years ago. And about 8 years after Hadoop originally came out, the version 1 was becoming stable. A little later, HDInsight became generally available, and then shortly after we saw that Hadoop 2 actually came out. The year after that, HDInsight version 3.1, running on Hadoop 2.4, was released, and that's sort of where we are right now. We've actually got another version of HDInsight called 3.2 with Hadoop 2.6 underneath. But I will actually be using this specific version for the demos. If you take a look at Indeed.com, which it's a job searching website, you can make some fun queries and look into the keywords that exist in the job postings that they have on their page, on their website. So I made I made some statistics and pulled out some graphs, and this one is showing the popularity and the increase of demand for Pig, Hive, MapReduce, and HBase, some technologies traditionally associated with Hadoop. And you see that all of them sort of really start to rise from about 2009, 10-ish, right? So that's when employers started to demand these technologies from employees. If you compare the success of Hadoop to 2 other technologies that sort of saw their rise since 2009-10, Android and iPhone, you see that it's actually rising not as much in absolute terms, but if you take a look at it in relative terms, you see that it's actually rising a lot more. So if you want, a high-paying job, doing some good stuff or some interesting stuff, maybe you should take a deeper look into Hadoop because it's really increasing its demand out there right now. If you couple that with R, which we're going to talk about today, you've really got two strong tools because we've seen that there's an increasing demand for Hadoop skills out there. And then if you couple that with R, which is by far the most popular tool for statistical analysis, I think you've got a very good skill set in front of you. So, okay, Hadoop in the cloud. We've got a cloud. It's called Microsoft Azure, and it offers a very wide range of services. Virtual machines is maybe sort of the very core thing that we've got, but we've also got a great hosting of websites and mobile services and storage and a bunch of other things. And in this very long list of services, we find HDInsight, which is, let me just skip ahead here. So here it is. It's a screenshot of HDInsight from the management portal. It's a platform as a service solution that's based on Hadoop, and it's actually based on the distribution that Hortonworks has made. So it's based on HTTP, running on Windows servers. And in here you can spin up a Hadoop cluster extremely easily. It will take about 10 to 15 minutes depending on how big of a cluster you want to provision. And it's just, if you compare that to the effort it would take if you would have to, buy your own servers and put them all into a network and install Hadoop on top of all of them, well, it's just, it seems like a piece of cake. We've got this thing going for us, and we support R in there. In fact, we've actually bought the company that implemented R Hadoop, which is called Revolution Analytics, and this was just 3 months ago. And if you do not know Revolution Analytics, they've got a bunch of different products. One of them is a enterprise product, a very great editor for R. And maybe this is not public yet, but I'm guessing that since we've bought Revolution Analytics, we've already got a very great IDE out there, Visual Studio. So I'm thinking it might be possible that we would combine the two things to offer a very great experience for developing R-based solutions, possibly connected to HDInsight, so that we as Microsoft can offer, the end-to-end R development experience. Let's talk about HDInsight. R Hadoop is a package you can install on top of Hadoop, and it offers the integration between the R statistical package and the two core components of Hadoop, namely the distributed file system and the MapReduce computation engine. It will move algorithm execution a lot closer to the data, and then the demos will do. I think that will become very obvious. It provides access to a lot of high quality statistical libraries, and I'm sure that the R users in here will know that. And it speeds up things by processing things in parallel, and that will become very apparent when we go through the demos as well. The demo will be based on the base example of MapReduce, the word count example. Who has not heard of this example before? About half? Okay. So I think this is sort of the hello world of MapReduce, and I think it presents, or it explains the idea of MapReduce very well. So in this case, we've got a challenge. We've got a bunch of text, and we would like to count the occurrence of each word in this text. And this is a great problem to solve with something like MapReduce. And this illustration illustrates it very well. So we've got some input over here on the left-hand side, and the first thing we'll do is split up this data so that we can push it out to the different data nodes and let them do the work. So this is where the idea of parallel processing comes into play, and we'll do a simple type of split. We'll split it by rows. So we've got 3 jobs out there, and the first job for each node would be to map the words that we've got in the text. So it takes this text as input, and it returns a list of key value pairs, where the key would be the word, and then the value would be 1. Okay. So even though that we in the second line right there have a line called car river, we still we do not group car into one key and then with a value 2 yet. Right now we just want to map out all the words. So it returns a list of key value pairs for each of the input texts, and then it moves on to an optional step, which is shuffling. It's not required, but it can in some situations it can speed up the processing. So what we basically do here is we group the keys so that it will be much easier to reduce them in the third step, and that's basically where we take all of the keys and we group we sum up the values, and then we stitch everything together and produce the final result. Okay, so that's I think thinking of the word count example will work very well for you when you work with MapReduce. It's a very nice example of how the technology works. However, it has one disadvantage, and that is every time we do something, we take something from disk, we process that in parallel, and then we write out the intermediate results or the intermediary results onto disk again. And if we were to put in the shuffling step here, we would have another step of reading and writing to disk, which is not something we would typically want because it's an expensive operation. If you've heard about Apache Spark, that's gotten a lot of popularity and a lot of traction in the ecosystem right now because it solves this problem to some extent because it works with in-memory technology instead. It saves the intermediate results to memory rather than to disk, and it just speeds up things by a very large factor. In fact, they've had competitions between traditional Hadoop clusters and then Apache Spark-based clusters, where they had to process the same amount of data, the same challenge, and the Spark cluster could do it by, I think, 1,000 times faster than Hadoop. So yeah, but we'll be focusing on good old MapReduce for now. And I think we'll just go straight to it now. So as I said, we've got many different services inside of Azure, and this is what the portal looks like right now. There is a new portal coming up, and I think I'll just show you this before I forget it. It's a little more modern. It's a little more, it works. It's got this very nice tile interface. But for now, you cannot, where is it? For now, you cannot work with HDInsight in here. So it says that we're working on adding services to the new Azure portal, but we're not quite here. So we still have to use this old or the current portal. If you do not have access to Azure, you can sign up for a trial and you'll get more than 1,000 kroner, which is enough to run a cluster for some amount of time so you can play with it. If you've got an MSDN license or an MSDN account, which I think you might have, right? You get free access to Azure, I think $150 a month, where you could also play with it. And then in the end, you can also purchase, pay for it, right? Or pay for it. Over here, I'm clicking into the service called HDInsight, and you see I already have 3 clusters up and running. The first one is a very basic cluster based on Hadoop 2.4. So that's version 3.1 of HDInsight, and it's got nothing but the basic packages installed. Then I've got a cluster with Apache Spark installed on top of it, and then I have my R Hadoop demo right here. The way to create a cluster is extremely simple. You click New, and then you say Data Services, and then HDInsight, and you can then choose either a plain Hadoop cluster with some of the most common packages installed already, such as Hive and Pick and stuff like that. You can also choose an HBase or a cluster with HBase installed and one with Storm. There's also an option to custom create one, and I think I'll just make a demo. Let's just say Copenhagen R demo. I would run this on Windows Server. Linux will become a option soon. And then I want to choose 3.1 because that's Hadoop 2.6. I want to use that. Here I get to choose how many data nodes that I would want in my cluster. And by default it says 4, but you can either increase or decrease that. Obviously the lowest amount is 1. And if you create a cluster with just 1 data node, just know that you will actually have a cluster consisting of 3 nodes because you will have 2 name nodes or 2 head nodes and then the 1 data node. And that's going to affect your pricing. You can also choose the size of the head nodes, which is also going to, affect the charging or the payment of it. You'll have to select a username and password. And you can enable remote desktop. I'll show you how that works in a second. Sorry? Oh no, so I could choose, you could choose Europe as well, yeah. And I'll have to choose a storage account because remember I said before that it's not working with the individual disks of the virtual machines in the network. Rather, it's using this storage layer that we have inside of Azure. So we would have to either create a new storage account or use an existing one. And I think I'll just choose this one. Yeah, I'll create. Yeah. And then in here in the end, there's an interesting thing because you can add script actions. And there are already some scripts that are written out there. This is for installing something that might not come out of the box with Hadoop, but maybe you would want to customize your cluster in a specific manner. For example, installing R Hadoop or installing Spark or installing something else, or tweaking, I don't know, the block size of the data in the cluster. And this is where you can do this. So you can write a PowerShell script, or I think there are some other scripts available too. At least PowerShell script will work. And this gives you the flexibility to customize your cluster if you want to go down that route. If you want to install R, you need to copy in the URL for a script that's already been written to install this, right? So once you've done that, you click OK, and then a cluster will spin up, but it takes a bit of time, so I cheated and already started up one. You can either connect directly to the Hadoop console through the interface, but you can also connect to one of the head nodes in the cluster through remote desktop, and that's what I want to do here. I already enabled remote desktop, so we can connect to it in this manner. You'd have to select a username and password, and we'll then log in. As you can see, I've already got some windows open here, and I think I'll just minimize everything. When you log for the first time into the head node, this is what you see. So you've got the Hadoop command line, plus you've got the links to some of the status pages that exist inside of Hadoop. For example, the status of the Yarn, the resource negotiator. If you've not seen Yarn before, it stands for yet another resource negotiator, and it was sort of the replacement of the job tracker we saw in the architecture before. And then because of installed R Hadoop in here, we've also got the R console, and this is not different from a typical R console. If I were to write something in here, I don't know, maybe 2 + 2, I would get what I would expect, and I can also save, I can make variables. This is a var.
You might want to make that a little bit smaller because we cannot see it.
Okay, 1 second. So how do I do that?
That's okay, just move it.
No, you just need to move with a little.
So if I do, is it better like?
Yep.
Okay, sure. Good. Okay, fair enough. So okay, so this is the console like you would expect it to be. Now the difference is that there are already some packages installed in R here that we could load into memory and then interact with Hadoop, the distributed file system, and MapReduce. And I've got a little cheat sheet here that I'll be using. So at its core, I think that map and reduce, those two functions in our MapReduce setting, can be compared very much to the two functions in our lapply and tapply. Everybody knows these two functions? Yeah. So it's about taking some list and then doing something with that list and return another list, right? So if we first of all take a look at lapply, we can look up the documentation for it, and it says that lapply returns a list of the same length as x, so the input, and each element is the result of applying a function to the corresponding element of x. So think back at the word count example again, right? We get some input and we return a list of key value pairs, and in that process we can do something to the value in the key value pair, right? In the case of word count, we would not do anything other than just assigning the value 1 to each of the keys. But to some extent, this is what lapply is doing. We've got tapply as well, and this is a function, it allows us to apply a function to each cell of an array, and it can help us reduce stuff, just like the reducer in a MapReduce algorithm. And we'll go through an example now, and I hope that the dots will connect. So I've got here a list of integers from a 1 to 1,000, and what I want to do with this list of integers is to apply a function to each value in the list of integers and then return back a list again. And I could do that with lapply, right? So I take the list of integers as an input and square them all, and I would then get this list of integers where I can see that the number 992 squared is equal to that number down here. This is what I would argue is my mapper, and I have a small example of that. So if we were to take that list of integers and put it into the distributed file system, we can use a function called 2.dfs if we include the library rmr2, so that's r MapReduce 2. It allows us to take a local variable that's in memory of the PC that we're on. So the array or the list of integers there is in the memory of our head node. We're then taking that and putting it into the distributed file system, actually placing that that data on disks in the distributed file system. If we wanted to, we could go back into the management portal of Azure we saw before, click into the service called storage, and actually look up this data and take a look at it right there. But I'm not going to do that right now. I've again got this MapReduce function, and it takes a little while to actually run, so let's just speak of it while it's running. There's a MapReduce function that comes with the RMR2 library, or the RMR2 package, where you define the input, and then it's required to define a mapper, but not required to define a reducer. You can do that as well. But here we're just, using MapReduce as its core. We're pointing to that data we just moved into the distributed file system as the input, and then we've got this mapper function where we don't really care about the key, we only care about the values in our list of integers, and then we return a list of key value pairs, and we define such a key value pair by cbind, where the key is the value of the integer, so the integer itself, and then the value of that key value pair would be the integer squared. Okay, very simple example. It should not confuse anybody, but it shows like what the mapper is actually doing. And if you think of the lapply function, this is basically the same, other than the fact that it takes a lot longer because there's some overhead into running these MapReduce tasks. Yeah, I think while this is running, we might actually take a look at where the data is stored. So as I said before, you can go into the management portal, and I've got this account called R Hadoop demo, and in here I've got a container called R Hadoop stuff, and this is where we can see all of the samples that are being installed with an HDInsight cluster by default. There are some logs in here as well. And we've got all of the apps that are installed in the cluster. They are also placed in Azure Storage. So we've got tests here, and I think we've got some more stuff, but we can just see tests here. And then if we go down to I think TMP, this is where these are the actual files that are being put into this system, and I think we might actually see that right now. So the MapReduce, or the MapReduce task just finished here, and we can see that the output has been placed at this path. So it's called file D something that ends with A6C, and we could actually go ahead and find that actual file. 8. Maybe we'll have to refresh. Let me just see 1 second. I think we might have to refresh this page, but you could go ahead and actually see the actual file here and download that if you would want to. It's not in clear text, it's in binary, so it wouldn't make much sense to open it in a notepad editor, but you know, this is where it actually is. So I think this helps to increase the transparency a little bit. Now, when we ran this, we defined a variable called output, and this is actually just a pointer to where this result is placed. So we can't just, if I would just type output here, I'm not getting the actual output. I would have to load that out from the distributed file system again, and I can do that by the from.dfs function. So I would say from.dfs, and then say what I want to get out is output. And it will then go and query the distributed file system, or in this case Azure Storage, to get out the file and print it out into the console. And it takes a little bit of time as well. Yeah, but what we should expect to see would be just what we saw when we used the lapply function before. I think it's okay so far. Are we going too slow? Is it okay? Okay, good. So here we see the result. It's formatted a bit differently, but basically we see this list of key value pairs where each of the keys is an integer in our list of integers, and then its value is its value squared, or the integer squared. Now let's move on to take a look at tapply, or actually use tapply, and I'm gonna generate a distribution, a binomial distribution here. So I'll do that by the rbinom function. Is everybody familiar with that one? Yeah. So I will flip a coin 100 times, and I'll do that 50 times. So I'll do 50 experiments, and I've got a very old rusty coin that's not perfectly balanced. So sometimes it lands on the other side more than the other side, and that's why we've got a probability of 0.45. If I run that and I type groups, I can see all of my 50 experiments, and then see how many times the coin landed on, let's say, heads, right? I can then apply tapply to get a set like this, where I basically see how many times did each of these values occur. Okay, so how many times was it so that I got heads 39 times? That was 4. So in 4 experiments I got heads 39 times, and in 5 experiments I got heads 43 times. Okay, does that make sense? Okay, so in some way the tapply here is reducing this set of data here to a smaller and more organized list of key value pairs, where the key is the number of heads that I got in a given experiment, and the value is how many experiments did I get 39 heads in. I hope it's not too abstract what I'm trying to say. Okay, so we did that with tapply, and I'll show you how it's done with MapReduce. So let's fire off this thing and let's take a look at it. So first of all, it has to move this data that I've got in memory on the head node into the actual distributed file system. So that's what I'm doing with 2DFS. And then second of all, I want to run this MapReduce function where I take the R data as this thing as the input. I define a mapper function where I take each of the values in my set and then I put a 1 next to it, just like in the word count example. This is actually not very different. The reducer is then taking all of the keys, so all of the values that we see right here, and it then sums up how many times that given number of heads occurred. Again, just like the word count example, but we're just using a binomial distribution here instead. Did I run this? No, damn. Okay, so that's what the reducer function here is. I've put it all into a from DFS function call. So the computation it will do, it's going to put that to disk, and then straight out after doing that, it's going to return that result out into my console. And hopefully it's not going to take too long. Yeah, let's speak of another thing while this is going on. You might know that this is all actually available on GitHub. Whoops. Let me just make this a little bigger. So Revolution Analytics has contributed a lot to the open source space of Hadoop-based packages, and RHadoop is one of them. So under their account, you can find both RMR2, RHadoop, and I think also RHbase and RDFS. The one we're using here is RMR2, which is dependent on some of the other packages. And in here, there is some docs and there is a tutorial. And the things I'm actually doing here is based on this tutorial. So if you want to go home and do this on your own, you can find all of this stuff in here. Let's see how it's doing. It's still computing. I'm thinking if I could show you something else meanwhile. While this is, would you be okay if we switch to another thing while this is running and then we switch back? Okay. So I'm not trying to confuse you very much, just a little bit. But we've got another service out here. As I said, we've got a very long list of services in Azure, and machine learning is another one. And in here, you can work with machine learning, you can work with R, plus a bunch of already implemented machine learning algorithms that we've made in Microsoft and offer to you through this machine learning studio. So it's a interface, or it's a studio that has an interface that reminds, or that is very similar to SSIS, SQL Server Integration Services, if somebody's worked with that. If you haven't, that's okay too. I've already created a R model here, and this is what it looks like. You've got this very nice and user-friendly interface where you can, pull in different building blocks and connect them together. So in this example, we've got some breast cancer data, and we can take a look at this here. This specific model is trying to determine whether a tumor found in a female's breast is either good or bad, or I think, yeah. So if it's godartet or onartet, I don't know how to say that in English. Yeah, exactly. And we can do that depending, or like from these different, or we'll try to estimate a model using R with this input data. And what we've got is some different things that we can observe on this tumor. For example, some things that I really don't know much about because I'm not, I didn't study medicine, but we've got some stuff that will allow us to, determine which class this tumor's in, either the good class or the bad class. So we're taking in this, and then we're, moving the data on, and we're splitting it up because we want to use some of it, 75 of it for training the model, and then the remainder, the 25%, to actually score the model afterwards and see how well it's doing. We're training a model built with R, but we could have chosen a classification model in here. For example, a 2-class neural network. I think this could do the job very well as well. But in this case, to show you how R can be implemented, I've created an R model instead. And what I'm doing here is I'm using a naive Bayes, which I'm not going to go into because of time. But I'm building a model here, and this model is going to be the output of this box right here. So we've got an untrained model that we can then move on, or then we can pass on to the next block, which is training it using this data we've got from the split function. And then afterwards, we're going to score the model to see how well it's doing. And in the end, I've added a Python script because some people are interested in that as well. But we don't really need that. So we could actually delete this thing. Let's try and run it and see if we can achieve some results that are satisfactory. Let's just see. Okay, so it's split up the data and it's created the model. Now it's training it. And it will take just a few seconds. It's trained, and now it will go ahead and score the model to see how well we're doing. And I'm pretty sure that we'll be doing fine because I obviously made a good model. So let's see, come on. Good, so it's done, and we can then visualize the results. So we get here, two other variables here that were not there before, and this is basically our guess on, like, is this actually a good or a bad tumor. So that's what this is. I think the actual model and the actual data is not that interesting. I just wanted to show you that it's very, very easy to implement R-based models in this service we've got here, Azure Machine Learning. Yeah.
But you can run that on top of Hadoop.
I could as well. So I just wanted to show you, that's why I was asking if it was okay to switch over to another service, because basically Hadoop and Azure Machine Learning are two very different things. Azure Machine Learning is not based on Hadoop, it's based on something else. And I think Azure Machine Learning is a little more accessible if you just want to work with data processing and statistics and maybe not, optimize a really cool cluster that can do, stuff for you in the specific manner you want. So Hadoop is a little more involving. You can do the same types of experiments on top of Hadoop, but it requires a little more from you, both as a developer and maybe also as a statistician, whereas Azure Machine Learning is a little more accessible in some ways, if you just want to do machine learning. Remember, you can do much more in Hadoop as well. Yeah.
So this model is running on a server in the cloud?
Yes.
And pricing would be how much data points or?
So actually, the reason why we built this, you can do these types of experiments, and if you're just interested in this data or the trained model, you can go ahead and download that, and you'd be happy. What we like, the reason why we've built it is for customers to build models like this and then publish them as web services. So we've got banks that have built models in here where they take credit card information as their input, and they've trained a model to detect whether that credit card is fraudulent or not. So it's a credit card fraud detection system. And so they build that model, and then in the end, it's basically a classification problem, right? Is this credit card fraudulent or is it not? And you would want to return that and pass that information on to another thing in your system. So imagine maybe if you were PayPal, right? You would have your website and you have your payment gateway. You want to check if credit cards that are being entered into PayPal or into your system are fraudulent. So you go ahead, you ask a web service, which can be generated here. I can actually do it right here. So you see this very nice graphics. We get some web service input and we get the web service output. I think in this case, I would not want my web service input to go in here. I would want it to go right in here. So I use my training data up here to train my actual model, and then when I create this web service, the web service is the model is being applied straight to the web service input. So the stuff that I would get, or the credit card details I would get from my payment gateway, and the result would come straight out of this scoring here. And this costs money per request. So this is really where we see that, right? So you can use it for other things and not use the web service part. That's totally fine. It's going to be a lot cheaper for you, but yeah, I think it's been built with this web service thing in mind. Now we've spoken a lot, so I think we should jump back to Hadoop and actually see the results. And as you see, we've got the results right here, and they're not very different from when we did our t-apply. Right here. Let me just see. Let me just do this again. So let me just try to fire off this thing again. So you see what we got from, well, obviously it's a different binomial distribution now, so we're not going to get the exact numbers, but the format is going to be very similar, right? Okay, so I think with those two concepts, map and reduce, and comparing them to lapply and tapply, it's going to be a good start for you to work with R on Hadoop. And I think, let me just check if I've got some other stuff. I think I do not. Do we have any questions? Yeah?
Now, when you use the HDInsight, it's very easy to make a service. If I want to do predictions in HDInsight,
yeah.
Can you make a service like that also?
You could. So the very, very simple way of doing this would be to build something that takes the results out of Azure storage, because that's where they're placed, and work with them from there. But I think the reason why we see a Hadoop ecosystem that's so wide and so diverse is because people get needs like the one you say right there, right? Oh, we want a nice way to put in data into our Hadoop cluster and then also retrieve that data in some way. So there is a project called Storm that's been developed for streaming data into a cluster and continuously train a model, for example, a credit card fraud detection model or whatever it might be. And there are also ways to get data out of Hadoop again very easily. Hive is one example of that, where we can use a language that's familiar to a lot of people, SQL, to query that data out again. So you would probably want to configure your Hadoop cluster in a way where you use more than just the core components that we've used right here. Yeah. Yeah. Any other questions? Yeah.
What happens to intermediate files after like every run of
yeah.
reduce or something?
So I think the intermediate files will actually be deleted from Azure storage, so it doesn't take up any space. But I think you should know that the specific service right here, storage, is probably the cheap. I think it is the cheapest service. So it's not.
Here, like right now, Microsoft is hosting unstructured data, like what you call big data for free.
Yeah.
So.
Oh, okay. I'm not sure which service that might be. So there is a cost associated to storing stuff in Azure storage, but if you take a look at the pricing calculator, there is one where you can estimate how much things are going to cost you. So if you would want, let's say, I don't know, 1,500 gigabytes, it would cost you under 200 kroners per month.
Yeah, I read some of the pricing plans a couple months ago, and they said that Microsoft is hosting this unstructured data. Whatever they mean by that.
Yeah.
So,
okay. It's good you say it. I have to look into that. I'm not sure.
Document DB.
Oh, okay. That could be. Okay. So there is a. I think it's down here somewhere. Where is it? It should be here. So we've got another service in the list of services. It's called Document DB. It's a document database, just like Mongo, but implemented in Azure and also developed with scalability in mind. Something that can be hard with MongoDB if you've ever worked with that. So problems like sharding and stuff like that is not going to be something you would need to think of because it's built into the Document DB product. Let me just try and see if it's here. Because I can't. Why is it not here? Let me just try and see. Document DB. Azure pricing, because I think you might be right. I think storage, yeah. So I think storage is free, but you would pay per request. So that's where it might come in. Yeah. Yeah. Got more questions?
So storage and the machine, I think those are two different services.
Is this, sorry, which?
So the machine learning thing you showed before, area. And storage, those are two different services you have to pay for separately.
Yes. So.
Right. But they're connected and you need both.
You need both, right? So here you can either upload a data set. If you had, I don't know, a large CSV file or something, you could upload that right here. But maybe you would build your, let's say, either your breast cancer detection model or your credit card fraud detection model. You'll build that up here, and maybe you would want to push in data continuously to, continuously train your model and make it better. And then uploading a CSV file every time might not be the nicest way of doing things. So what you can do instead is to use a reader, and this reader can read from either blob storage, the service I showed you before, table storage, a SQL database, a Hive query that might come from Hadoop, or some REST interface you might find on the internet. And there are ways of both training your data, training your model, and also consuming your model, like I've tried to do here with these two inputs and outputs. Yeah. Yes?
Did you say that R would be a part of Visual Studio?
So I don't think I'm officially supposed to say that, because I'm just thinking, we buy this very active player in the R space, Revolution Analytics. And they've got a great editor. We've got a great editor, not for R, but for other stuff. Yeah, and if you've worked with Visual Studio, you know that we're trying to take everything we do, whether it's Windows Phone development or web development or whatever it might be, we're trying to put that into the same IDE, and that's why I personally think that we might see something like R in Visual Studio.
So the next question will be, will there be an Express version?
So there's actually, we made a new model. We still have Express versions, but we went over to this community edition. So it's free now. You can there are like some rules for what you can use it for, but it's basically a Visual Studio Professional for free. So it's about $6,000 that we're giving away per year. Yeah.
This R in the cloud is using regular R distribution or this Revolution R?
So I think it's the core is the open source, the regular, and obviously those packages you need to run R in MapReduce are the ones that come from Revolution Analytics. Yeah.
What if you want to install more packages? Because usually when R running, you found a package online and you want to install it.
Yeah, so you can do that. There's no problem in doing so. So if you want to work through the R console, because maybe that's what you're used to, I suggest you to do exactly what we've done here. Log into the head node and open up the R console, because that's where you have access to all of the cluster. Yeah.
And then when you set up the Hadoop or system, you select the number of nodes. If it was 4, how do you know how many you have to do? Or
so
because I guess you pay according to that.
Yes, that's a good question. We could actually take a look at it. So those hyperlinks that were out here on the desktop, you can actually look a little more into what nodes are doing what job. So things have been sort of abstracted away from us so far, because we're just interacting with the cluster through the head node. But if you take a look at some of the MapReduce jobs I've just run here, I can click into them and see which nodes are doing what job. And in order to determine how many nodes you need, I think it depends very much on the type of work you would need to do. If you've got very large data sets that require very heavy processing, it's kind of obvious that more nodes is going to give you faster results, right? In this specific case, I just have one data node, which does not make a lot of sense, right? So I would say it really depends on your budget, because it can become a little bit expensive if you have many nodes in there. Yeah. Any other question? No? Yeah.
You have the usual parallel trap. Whenever you're playing parallel stuff, you do miniature examples, and everything is killed by overhead. So we see you doing something that's done like that in planar and takes a quarter of an hour using Hadoop. Do you have some examples where things are scaled up to a reasonable size so you could see sort of benchmark? How much do you gain from this?
I think that's a great suggestion for something I should do next time I present this topic, because I don't have anything prepared right now. But I think it would not actually be very difficult to find some good examples on the internet that you could implement. I think normally when I have to explain what big data is to other people, or at least to customers, enterprise customers, they're not always the smartest. Like sometimes you have to explain it in basic terms. So whenever you've got so much data that it can't run on just one machine, where you have to set up some sort of cluster to run things, that's when it becomes feasible. So obviously the examples I've done here, if that's the only data I have, it's not a good idea to spin up a Hadoop cluster, right? Because it's faster to do on your own PC. I don't know how to give you a more
what's sort of what happens if you do it on a bunch of 500K array chips or whatever?
Oh yeah, so
sort of. What would the pricing be like? Where are we? What's the real world application?
So I think, for example, RDBMS like SQL Server, for example. If you develop a solution using SQL Server analysis services, which is our tool for business intelligence, if you've got something that can fit on one server, then I think SQL Server is going to do a much better job, processing the types of queries you would have. But you should start considering Hadoop when the stuff you want on your server can't fit on it, right? So I've built a solution on Hadoop with some of the salespeople we have in Microsoft, because they also they need to answer the question you have when they go out and speak with customers, right? And so we've built a Hadoop cluster using Storm to consume the Twitter fire hose. So we're getting tweets in, and it's just over time it's becoming the data is growing so much that it just cannot fit on a single server, right? So I think Hadoop is something you should use when your single SQL server cannot do that job. Yeah.
The HDInsight, to get back to that one.
Yeah, sure.
Usually what I would do with a machine learning algorithm was that I would like to feed a lot of data into it.
Mm-hmm.
So I kind of thought that you would feed it into Hadoop and then you would work with the data.
You know what?
So what is the recommended solution if you have really a lot of data?
Yeah, I think I'm getting good ideas for how to improve this demo in the future. So we actually we had this reader right here, right? Let's say that we would consume data from a data source that's just giving us tons of data per second or per hour or whatever it might be, and putting it into a SQL server is not feasible for some reason, right? We could put it into a Hadoop cluster and say, okay, Hadoop, we want you just to host our data. We want to use the distributed file system that Hadoop gives us. But we are not necessarily interested in running our queries on top of, or using MapReduce. We might want to do that in Azure Machine Learning instead. So a way to couple those two different services would be through Hive. So this reader component here supports Hive, so you could write a Hive query to extract the data that you might have in your Hadoop distributed file system, and then use that in your R model or in your machine learning model.
How much data you can read into an experiment like that? So
yeah.
Then you use Hive to do a sample of your data, or?
Yeah, so it's a good question because it's maybe not feasible to load in, I don't know, terabytes of data unless you've got.
I think the limit is 10 gigabytes.
Yeah. those are good questions that I should look into and possibly get your email so I can give you a better answer than right now. But yeah, short answer, connecting Hive to, or Hadoop to Azure Machine Learning would be through Hive. Yeah.
I saw an interesting blog post somewhere that said, provocatively, your data is not that big, which actually meant that if you had data like 5 terabytes, something like that, then it was a case for Hadoop, and if it was anything less, just invest in a bigger desktop with lots of RAM.
Yeah, but you know, it's kind of like, I don't
That's
know.
also the problem of unstructured data.
True. Yeah, so that's another thing, right? But it's kind of like, I don't know, I think data is kind of like guys and their relationship to their, you know, male parts, right? Everybody wants a bigger one, right? So it's the same thing with data, I think. I've heard some crazy things when I've talked to customers, like people would say, my Excel spreadsheet is like, or Excel is going into not responding when I open this Excel spreadsheet. This must be big data. Well, it's like only 10 megabytes big, so I don't know if it's that big, you know. I think the perception of big data is very, I think 5 terabytes might be a good threshold. I typically just think when one computer and one server can't do the job, when you need to scale out in some way, that's when you can start talking about it. And I think 5 terabytes might actually be that limit, because you can install, you know, 1 terabyte disks in one PC and still work. But more than that would be, I think, difficult. Yeah? Yes?
One last question. It's kind of technical. Can you run a process on GPU instead of CPU?
Not here. So
you can run stuff like Theano.
So in the case of Hadoop, for example, the types of virtual machines we have there do not have graphic cards installed. So yeah, unfortunately, no.
Clear answer.
Yeah. I think we're working on that though.
It definitely has its advantages.
Yes, I know.
For picture processing or sound processing.
Yes, that's true. Yeah.
Right.
Yeah. Okay. I think we'll wrap it up then. Yeah. Let's just wrap it up, and it's done.
Thank you.
Yeah.